Modern data centers usually consumes enormous amount of energy, and we take some well-known data centers like AWS and Microsoft as an example. Based on some ground statistics of the electricity bills, we found that these data centers usually consumes $20 to $100 million per month to maintain their own data centers. Therefore, to provide a eco-friendly environment and simultaneously reduce the expenses on the basic maintenance, we come up with the idea of dynamic right sizing. The key concept is straightforward. We just turn off unused servers and wake them up again when the demand increases. And to use this method, we proposed a mathematical model that could quantify the cost of the data centers. The model is composed of two parts, the operating cost and the switching cost. The operating cost is a cost due to the delay of using fewer servers and also the energy cost for maintaining one active server with a particular load. The switching cost is the cost incurred from toggling servers into and out of power saving mode, which is dynamic compared with the operating cost. And to use this mathematical model, we have the problem of discretize the time into a bunch of time slots. And assuming that we have knowledge of all time slots, we can have a good estimation offline. However, to really use this algorithm and solve the optimization problem, we need to come up with an online algorithm. And from here, I will switch to Suman for more in-depth discussion.
Hello. So in this project, we explore dynamic right sizing in data centers, the problem of matching server capacity to fluctuating workloads while minimizing both operating and switching costs. The traditional approach, receding horizon control, uses short-term workload predictions to make decisions. While theoretically appealing, it's sensitive to forecasting error and system parameters, making it unstable in practice. On the other hand of the spectrum, the optimal offline solution assumes complete knowledge of the future workloads. It delivers the lowest possible cost by planning globally and changing capacity only when necessary, but it's purely theoretical. Our focus is on the lazy capacity provisioning, a practical online algorithm that mimics the structure of the online solution, of the offline solution without needing predictions. LCP works by maintaining upper and lower bounds on feasible capacity and adjusts only when the current server level risks violating these bounds. Despite its simplicity, it's probably three competitive and performs remarkably well on real-world traces, even with zero look ahead. What's compelling about LCP is that it strikes a balance between performance and deployability, offering near optimal results with minimal assumptions and low computational overhead. Yeah, that's all from me.
For the experiment, we evaluate the lazy capacity provisioning, which is LCP algorithm, under two real-world workload traces. The first is from the Hotmail, which shows a relatively stable and smooth load pattern. Even during the nighttime, the activity remains steady due to the background process like backups. The second dataset is from the MSR Cambridge, which has a more fluctuating load with noticeable drops during the off-peak hours. Now, in terms of the results, first, regarding the prediction window size, we find that even when the available prediction window is very small, 1 or even 0, LCP still performs significantly better than RHC method. This shows that LCP doesn't rely heavily on accurate forecasting to be effective. Second, looking at the peak-to-mean ratio, in scenarios with pronounced peaks and valleys, like what we see in the MSR dataset, LCP is particularly effective. By shutting down servers during low demand periods and scaling up slowly during spikes, LCP managed to reduce total cost efficiently, even when challenging high demand workloads. So overall, those experiments highlight LCP's robustness and adaptability in both stable and dynamic data center environments. That's all for our presentations. Thank you.